Hi everyone. Welcome back to Dave's Math Channel. Today I'm going to talk about a very important result in number theory known as Fermat's Little Theorem. This is not to be confused with Fermat's last theorem. I think you guys probably know Fermat's last theorem, x to the n plus y to the n equals z to the n, has no solutions in integers where n is an integer greater than 2. Fermat thought he had a proof of that one. He said he didn't have enough room to write it down, and I think you guys know the story. Nobody found a proof until Andrew Wiles in the 1990s, which was over 350 years after he originally came up with his so-called theorem. That's his most famous quote theorem unquote. Although nowadays I think practically nobody really believes that he actually proved it because Andrew Wiles' proof was very, very complicated, over 100 pages long, involves some really complicated math. I already made a video about that. That's not the subject of this talk. The subject of this talk is another very important theorem due to Pierre Fermat's Little Theorem. This one is much easier to prove, and Fermat actually did prove this one. And I say what the theorem says on this slide. It says a to the pth power is congruent to a modulo p. Um, and I have it written out a little more detail here. So here's what it says. P is supposed to be a prime number, any prime number. I'm sure you guys all know what primes are. So I want to explain that. A is any integer. And if that's true, if P is any prime and A is any integer, then A to the P is congruent to A modulo P. What that means is if you take A to the P minus A, that is always divisible by P, no matter what A is, as long as A is an integer and P is a prime. And I'll give some examples that show that later. But in particular, if P does not divide A, in other words, if A is not a multiple of P, it's pretty easy to see that if A is a multiple of P, this holds, because like, you know, if A is already divisible by P, then A to the P by P is 0, because A to the P is already divisible by P. I mean, A is already divisible by P, which means that A is congruent to, A mod P is 0, which means that A to the Pth is also 0 mod P. So that case is pretty trivial. But the more interesting case is when P does not divide A. In that case, we have a little bit stronger result. It says A to the P minus first power is congruent to 1 modulo P. And this is actually how we usually use this theorem. This result isn't so obvious, but it is true, and it's a very, very useful result, as I'll show you in a few minutes. And there's two kind of classical proofs of this theorem. They're not really that complicated. There's one proof that involves the binomial coefficients in the binomial theorem. You guys might have learned this in high school. So the binomial theorem just says if x and y are any numbers, that x plus y to some power, x plus y to the n is the sum of n choose k times x to the k times y to the n minus k. I'm sure you've seen that. And so you can do a special case of that here, which is what they're doing on the top line. In particular, if we use k equals p, where p is a prime, then look at the special case where a is 2. So 2 to the pth power, we can write 2 as 1 plus 1, and then we can just apply the binomial theorem. So we just expand 1 plus 1 to the pth power in terms of a sum of binomial coefficients. It's just the sum of all the binomial coefficients. In other words, all the coefficients on the pth row of Pascal's triangle. So we write p choose 0, that's 1, plus p choose 1, plus p choose 2, all the way up to we choose P, which is also 1. And if you add all those up, I mean, the thing to notice here, this is another fact about binomial coefficients. I don't want to prove this. It's pretty easy to prove. But it turns out that P choose K, as long as K is not 0 or P, P choose 1, P choose 2, all these two coefficients are all divisible by P. This is pretty easy to see. I mean, there's a formula for the binomial coefficients. Like I said, this talk might be a little bit technical for you guys. I assume you know about binomial coefficients. Maybe I can give you an example. Like suppose P was 5. then these numbers would be 1, 5, 10, 10, 5, and 1. And notice that all the coefficients in the middle are all divisible by 5. 5 choose 1 is 5. 5 choose 1 is 5. Choose 2 is 10. 5 choose 3 is also 10. And 5 choose 4 is also 5. And that's true whatever p is. So the point here is that we can ignore all the terms in the middle because they're all divisible by p. Remember, in the end, we're taking everything modulo p, and what we're left with is that 2 to the p is congruent to 2 modulo p. So it works when a is 2. And to complete the proof, you can just do what's called induction, mathematical induction. So you can assume that it's true for some a, and then prove it's also true for a plus 1, which is what we do on the bottom line here. So assume that a to the p is congruent to a modulo p for some in a that's not divisible by p, and let's see that it proves also holds when a. Actually, yeah. So actually, you don't even have to assume that a is not divisible by p. A is an arbitrary integer here. So we've proven, we're assuming that a to the p is congruent to a mod p for some integer a, arbitrary integer a. And then we also want to prove that it's true for a plus 1. So again, we use the binomial theorem. We expand the a plus 1 to the pth power in terms of binomial coefficients. And again, you'll notice that all the binomial coefficients in the middle here are divisible by p. So we can ignore those, and we're left with just a to the p plus 1. Well, we already know that a to the p is congruent to a mod p. That's what we were assuming. So voila, the result is that a to the plus 1 to the p is congruent to a plus 1 modulo p, and we're done. That completes our proof by induction using the binomial theorem. It actually turns out there's an even much easier proof than this if you know some group theory. Here's the easiest proof I know of. So the thing you're supposed to notice here, if you know a little bit of group theory, then you can consider all the powers of a from a to the 0, a to the 1, a squared, a cubed, all the way up to a to the p minus 1. Well, that set forms a multiplicative group. It actually, and since there's p elements and they're all distinct, that means that they have to add up to 0. I mean, so you consider this set here. Here's how we're doing. They're all different modulo p. All these multiples of a. Here's the set S we're writing down. We're writing down all the multiples of a modulo p up to a times p minus 1. If we assume that a is not divisible by p, these guys have to all be distinct. And then that means that they form the entire group, and they're all different. So that means a has to have an inverse. So, because a has an inverse modulo p, that means that this can say representative of 1. So if a is any arbitrary number in this group, it has an inverse, and that means that this whole set is the same thing as this set. And if you add all these, if you multiply all these numbers together, you get 1. That's another proof. So I guess you have to know a little bit of group theory to know how to prove this, or you have to know something about binomial coefficients. So they're a little bit technical proofs, but if you know a little bit of basic number theory, it's not so hard to prove either of these ways. Anyway, now I'll give you some examples. So let's suppose A is 20 and P is 7. We know that 7 is prime. Suppose we want to compute 20 to the 6th power modulo 7. Well, notice that 6 is 7 minus 1. So if we let a equal 20 and equals 7, then this is just a to the p minus 1, which by Fermat's little theorem we know is congruent to 1 modulo 7. So what this says is that 20 to the 6th power, which if you multiply it out is equal to 64 million, this says that 64 million has to be congruent to 1 mod 7, which is just another way of saying that 64 million minus 1 is divisible by 7. And you can do this division yourself and check this. It turns out that 64 million minus 1 divided by 7 is an integer. It's actually equal to 9,142,857. So it works for this case. And you can even do harder examples. I mean, you can use huge powers. I mean, suppose we wanted to find 7 to the 2019th power modulo 13. Well, you don't have to actually calculate 7 to 2019th power. That's horrendous. I mean, that's probably a number with like something like 1,500 digits. You wouldn't want to calculate that. But here's what you do. You know, because of Fermat's little theorem, that 7 to the 6th power, or 7 to the 12th power, that's p minus 1, p is 13. So 7 to the 12th power has to be congruent to 1 modulo 13. So you can subtract out all the multiples of 12 from 2019. So you just take 2019 modulo 12, and you notice that 2019 is equal to 12 times 168 plus 3. Well, you really don't care about the 12 times 168 because you can write that as 7 to the 12th power raised to the power 168 uh, times 7 cubed. But we already know 7 to the 12th power by Fermat's last theorem is congruent to 1. So now we have 1 to the 168th power, and 7 cubed is 343. And we can ignore 1 to the 168th because we know that's equal to 1. So we're just left at 343, and then we finally take that modulo 13, we get 5. So that's very easy. With hardly any work, we didn't even have to use a computer. Just using Fermat's little theorem, we can determine the remainder when we divide this huge number here, 7 to the 2019th power mod 13. We know what it's equal to. It's equal to 5. Pretty amazing. So it's a very, very useful result. Not that hard to prove and really, really useful. As a matter of fact, it's even used for RSA encryption. And there's a generalization that's used in RSA encryption. It's called Euler's theorem. So here, n now longer, the modulus doesn't have to be a prime. It can be any integer you want, any positive integer you want. But the only difference is instead of using n minus 1, you have to use this thing called the Euler-Toscan function, phi of n. I'm not going to say what that is. It's an easy function to compute. It's a number theory function. I might do another video on it sometime. But if you want to know a to any power, you do the same trick. It's just that instead of using n minus 1, you use phi of n. So this is a very useful result. As a matter of fact, like I said, it's using RSA encryption. So Fermat's little theorem is a very useful result. It can even be generalized to Euler's theorem. And anyway, that concludes my talk on Fermat's little theorem. I hope it was comprehensible to you guys. I know this is a little bit more advanced video than I usually do, but anyway, I just kind of wanted to mention this result. It is an important number theory result. So anyway, thank you for watching. Long live math, and I'll see you next.